Hello everybody, let's tackle video 2 of week 2. We are going to hit another pretty heavy topic, a relatively easy question, but it gets pretty deep pretty quickly and we're still left with a lot of mystery at the end. So the question we're going to tackle on this video is, what is matter? So before I bring up the slides, I just want to do a little bit of a thought experiment and use some scissors here. Here I have a piece of paper. What is it made out of? So we're going to be discussing what is matter. Well, we could just start making a catalog of all the matter out there, right? We have paper, we have water bottles, we have connection cables, we have cell phones, we have humans, we have dogs, so on and so forth. We have stars, we have galaxies, we have oceans. So we could just start making a list of all the things that constitute what matter is. Something that has mass and takes up space. But that would be a really long list, right? There's no way we could ever catalog all the types of matter. There should be some fundamental bits of matter out of which we can build all matter. So back to my piece of paper and my scissors. So if I were to take this piece of paper and cut it, I get a smaller piece of paper. I cut that in half, cut that half in half, that half in half, that half in half, and keep on going. If I were to keep cutting by half over and over and over and over again, I'm getting smaller and smaller bits of paper. And now I don't want to cut my finger. If I were to keep cutting, could I cut this down forever and I just end up with smaller and smaller and smaller and smaller and smaller and smaller bits of paper? Well, for most of us that now have lived in the world where we know about the atom, the obvious answer is no. Eventually, you find some stuff that you can't cut anymore. But what are those smallest bits that you can't cut? Now, let's go ahead and repeat that with my slides, but with a lot less words and more pictures. So we are trying to figure out what are the fundamental bits of stuff that make up everything. What is matter? So instead of a piece of paper, let's imagine we have this wonderful rock here, a special type of rock. This is an ordinary chondrite, a meteorite, a rock that fell from outer space and now we can pick up. It's the most common of all the types of meteorites, hence it's called ordinary. It's called a chondrite because you can see these little circular blebs in there that are called chondrules. So it is an ordinary meteorite that contains chondrules. We call that an ordinary chondrite. So if I were to take that rock and smash it up, bang, 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 smashy, 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 until it got smaller and smaller and smaller and smaller bits. And then I got something really nice so I could cut those smaller bits down smaller and smaller. Obviously, I wouldn't end up with just smaller pieces of meteorite. I'd end up with different minerals that make up that meteorite. So a tip of the hat to our geology folk. And then I could keep cutting and keep cutting and keep cutting. And what would I eventually cut down to if I had an amazing pair of scissors? Eventually, I'd end up with the bits of atoms that make up of this, the chemical elements. So for an ordinary chondrite meteorite, and no, you don't need to know this stuff, you would end up with stuff like silicon, magnesium, iron, oxygen, calcium, and a whole host of other things, other chemical elements in there. So clearly it's not rocks or turtles all the way down. Eventually you start hitting these elements that make up our periodic table of elements. There are currently 118 periodic table or elements on the periodic table. And when you probably learned about this, you learned that these are each element, the fundamental bit of each element is an atom. And it's an atom of a different element. So that sounded a little circular, but so a carbon atom is the smallest bit of what we call the element carbon. And we have 118 of them. So we've gone from a list of all types of matter, which we could not make because it's way too long, to now we have a list of 118, and these ones, most of these ones down here don't exist in nature. So we're down to a much smaller list, 100 or so elements, out of which we can build up everything that we've known or really interacted with. Myself included, water, table, my cell phone, all the rare earth elements in there. So that's pretty good. We're down to the periodic table of elements. But can we cut up atoms? Are we down to the fundamental bits yet, our elementary particles? So let's take a atom. We'll pick the carbon atom, which I have displayed right over here. And what is a carbon atom made out of? And now it feels like we're back in middle school science class. Like, I've learned this before. But just to jog everybody's memory, an atom, all atoms, are made up of protons, neutrons, and electrons. These protons and neutrons live in the nucleus. And then you have electrons, which orbit around the nucleus. This is the so-called Bohr model of the atom. It is not the current quantum mechanical model that we take, the electron cloud model, as some people call it. But the Bohr model will work for now. So atoms are made of smaller fundamental bits. There are subatomic particles. And those subatomic particles are protons, neutrons, and electrons. What makes an atom of carbon a carbon atom? It has 6 protons in its nucleus. So all atoms out there that have 6 protons in their nucleus are carbon. You have 1 proton in your nucleus, you're hydrogen. You have 26 protons in your nucleus, you're iron. So now we see that all the elements on the periodic table are made up of atoms of that element, and those atoms themselves are made up of protons, neutrons, and electrons. The number of protons tells us what element we are here on the periodic table. And that's really these numbers right here. So beryllium has 4 protons. Zirconium has 40 protons, and so on and so forth. All right, so subatomic particles. Surely that's it, right? And if that is true, we could take protons, neutrons, and electrons and make all matter, build all matter. So are these our fundamental particles? Is this it? Can we keep cutting, or have we cut to our smallest bits yet? Well, the answer is not all of those are fundamental particles. And this is pushing perhaps past what you've learned in your previous science courses. So we have our protons, our neutrons, and our electrons. Our electrons are fundamental bits. They are fundamental particles, what we normally call an elementary particle. There is no knife out there where you can cut an electron down to be made and see that it's made up of smaller bits, as far as we know. So we've gone fundamental. Electrons, fundamental particle. The protons and the neutrons, however, we can smash them up. We can cut them. And we don't actually have a pair of scissors that we go snip, snip, snip to cut protons. We put them in atom smashers, these particle colliders where we smash, say, protons and neutrons together, or 2 protons together, and we see what happens. Turns out they explode. So they blow up, and you'll see that they're made up of smaller little bits. So what are those smaller bits that make up protons and neutrons? They're little particles that we call quarks. And quarks are elementary particles too. Now, I'm not going to require you to remember these details, but protons and neutrons are made up of 3 quarks apiece. And the proton, what makes a proton is it's made of 2 up quarks and 1 down quark. A neutron is 1 up quark and 2 down quarks. And now we have fundamental particles. And in fact, using the electron and up quarks and down quarks, just 3 elementary particles, we can build every element on the periodic table, and then we can build Dr. Lindsay, we can build this table, we can build the oceans, we can build Jupiter, we can build pretty much everything that's made up of chemical elements, the elements on the periodic table. That is pretty amazing. Our list is down to, if you don't want to differentiate between them, basically 2 fundamental particles to make up with all the matter that you have probably ever thought of or certainly interacted with. Electrons and quarks. Build up every element on the periodic table and then start building more complicated things from there. Wow. But is that it? Is it just electrons and quarks? Well, now we get to stuff that I really don't expect you to remember, other than that protons, neutrons, are made up of quarks, which are elementary particles, And electrons is another elementary particle, but quarks and electrons are not all the elementary particles. So for ordinary matter, the kind of matter that you're used to interacting with, and the kind that you interact with every day, probably you have had very little experience outside of any ordinary matter. Well, you certainly have not had any interaction with outside of the ordinary matter, but there are more than quarks and electrons of the elementary particles. And in fact, there are 17 elementary particles, or I should say elementary particles of ordinary, regular matter. You do not need to know what all of these are, but here is a video and you're learning something new. We codify these 17 particles in what's called the Standard Model of Particle Physics. We're going to extend the standard model a little bit on the next slide, but we have things like our electron on here, but then we have other fundamental particles like neutrinos, muons, tauons, and then we have some more neutrinos. We have our quarks, our up and down quarks, but they're also charm and strange and top and bottom. So we have our quarks, we have what are called our leptons, then we have what we call our gauge bosons. And notice that the photon, the particle of light, is one of those. These are the particles that carry the 4 fundamental forces. So these are particles that are responsible for carrying the fundamental forces. The photon carries the electromagnetic force. And then we have our Higgs boson. Well, now this might seem kind of incredible, and that's because it is. This was theoretically derived, working all the way up until the 1970s, that all of these particles should exist. But we had not yet observed all of those particles. A theory predicted that these particles exist. And then through particle colliders, particle accelerators, like the CERN accelerator, and the Large Hadron Collider, we have systematically ticked off and discovered all 17 of these. So they were predicted, and now we've observed all 17. Okay, 17 bits of fundamental particles, except for every elementary particle has an antiparticle pair. What? And here, yes, I'm talking about antimatter. So every fundamental particle has its own antiparticle pair. So definitely you don't have to remember any of this, but this is the same as what we had before, same as this. And what we've done is for every one of these particles, we've put an antiparticle. And this is really what antimatter is. So let's use an example. And no, you don't need to remember any of this. So the electron has an antiparticle, the anti-electron, that's called the positron. Same mass, and almost down the list, same properties as the electron, except instead of a negative charge, it has a positive charge. You get those two things together, they'll annihilate one another and release energy as they convert that mass to energy. And to make things even weirder, in the standard model of elementary particles, some particles are their own antiparticle. So the antiphoton is the photon. The photon is the antiphoton. I know, strange, but not for this class. You should know, however, that there is the standard model of particles. It has 17 on there, and then we can do an antiparticle for each one of these particles over here. No, please don't spend time memorizing them unless you have designs on being a particle physicist. All right, so now we have categorized the ordinary matter, and we've even thrown in antimatter as a bonus. So what is the breakdown? If we were to take all the chemical elements, what we call baryonic matter, if we were to take a look at that, how much is there of each element? What are the so-called cosmic abundances? And up here is the kind of stuff that I would like you to know. Just in general, the universe round, ordinary matter, the kind of matter you can interact with, the kind of matter that's made up of electrons and quarks, by number of atoms, so if you're just going to count up the total number of atoms in the universe, 91% of all the atoms in the universe are hydrogen. 9%, or approximately 9%, are helium, elements 1 and 2. And you might be thinking, Dr. Lindsay, that adds up to 100%, but I put approximately there because less than 0.1% of all the other atoms in the universe are the elements that are heavier, more massive than hydrogen and helium, elements 3 and higher. And if you're really, really curious, I have the breakdown over here. This is by mass instead of by number of atoms. So the numbers are a little bit different because helium is roughly 4 times more massive than hydrogen. But this is all of our ordinary matter. And then we have our little bit of antimatter, which we pretty much have to create in particle accelerators. But if we start looking around the universe, and this is what Vera Rubin did, Dr. Vera Rubin, we'll see that somehow all this matter just doesn't add up to what we see. And I know this is a complicated plot, but I'm here to walk you through this. So right here on the x-axis, we just have the distance, and distance away from what? Well, you can see this wonderful image of a spiral galaxy right here, and we're going from the center of the galaxy outward. So this is distance from the center of this galaxy. And on this is how fast is stuff orbiting around the center of the galaxy. We understand orbits. So we know by how much stuff is interior to you, that will dictate how fast you're orbiting and how far away you are from it. So planets farther away from the sun orbit slower and slower and slower and slower. That tells us that we should be able to, based on all the matter that we can see, all the ordinary matter, all the luminous matter, that we should see this speed of stuff orbiting around, this dashed gray line. It goes up as we add more material, but eventually we can't see any more stuff at the edge of this galaxy. So things would orbit slower and slower, just like Jupiter orbits slower than the Earth. So that is what we would predict based on all the ordinary matter that we can see and observe. These dots right here, however, are what are observed. Yes, this is routinely observed. This is a recreation of the original observation that Vera Rubin did. And we don't see what is expected, what is predicted by ordinary matter. In fact, we see that it's a lot greater, that things are orbiting a lot faster than we expect. And it gets faster and faster, even after you go way out here and you leave all the ordinary matter, all the luminous matter. You leave that and you're just going out into space. So there has to be something that explains this difference between what we'd expect and what we observe. How do you get things to orbit faster? You have to add more mass. But we accounted for all the mass we can see. Oh, then there must be some mass that we can't see that doesn't interact with pretty much anything that we know about. But it does generate gravity, which makes these orbits faster. This is the original observation that Dr. Vera Rubin made to deduce and infer that there must be more mass in this galaxy than we can see, and that mass that we can't see, that matter that we can't see, we don't know anything about it. We don't know its properties other than that it's mass because it generates gravity. So it's dark matter. This was the original observation of dark matter. And you can look at the difference between what's observed and what's predicted to actually map out and get an idea of how much dark matter is there. There are other lines of evidence that show dark matter. They all line up, but this is just the original observation. So there's not only ordinary matter, the kind of stuff we can interact with, stuff that's on the periodic table, but there's also dark matter. And astoundingly, ordinary matter is only 16.6% or 67% of all the matter that's out there. Well, let's just call it around 20. It's easier to remember than 16.67. So about 20% of all the matter in the universe is ordinary matter, the kind of matter that you're used to interacting with. That leaves the other 80%. 80% of all the matter in the universe is this mysterious dark matter. We can only infer its existence because it's creating gravity, and we can observe the effects of gravity. We have no idea of what this dark matter, what the true nature of it is. There are a lot of people working on this, but we just know that it has mass because it creates gravity, and we can see those observational effects of that gravity like we did with how that galaxy was rotating. As far as we can tell, it doesn't interact with ordinary matter, light, or energy. So how are we supposed to really probe and observe this? We need some new physics to really understand what this dark matter is. And it's really important because as outweighing a 4-to-1 ratio, dark matter to matter, it is what shapes the structure of the universe. It is really what's creating all the gravity that gives our universe the structure that we see. So it's absolutely fundamental to our understanding of the universe that we live in. Okay, let's keep pushing. So now we have ordinary matter and dark matter. And there's more dark matter than there is ordinary matter. Well, turns out we need to account for another thing as well. If we're going to understand the universe that we observe, and we make observations of this, we have predictions, and then whenever the predictions haven't matched the observations, that allows us to infer the existence of something else. And one of those things is we can use supernovae explosions to see how far away things are. And we find out that the supernovae explosions really far away are retreating away from us faster than we'd expect for the normal expansion of the universe, which tells us that the universe is expanding at an accelerating rate. Weird. So how do you get something that to accelerate? That requires energy to change the motion of something. So there must be some energy out there that's causing the universe to expand at an accelerating rate. We don't really know what this energy is. Again, we're left in the dark in it. So we call this dark energy. And if we're going to account for all the matter and energy in the universe, and Einstein, via his E equals mc squared, told us that matter and energy should have an equivalence. So if we're going to account for all the matter and energy in the universe, we have to account for dark energy, which is 70% of the entire makeup of the universe, of all the components of the universe. So we have 70% dark energy, roughly 25% dark matter, and 5% ordinary matter. That's 95% of the universe that we pretty much know nothing about. Holy cow, that is a lot of room for discovery. We are just beginning our journey of understanding what matter and the universe are. And I want to go ahead and end this video with a little bit of eye candy, just to show you a little bit more of the evidence that we have, because I said that the dark matter is really integral for us to understand the structure of the universe. So I wanted to show you what the large scale structure of the universe is. So this image right here is a 250 megaparsec slice of a simulated universe, a so-called Bolshoi cosmological simulation. This is a grand simulation that was run on some of the world's fastest one of the world's fastest supercomputers a couple of years ago. And what it did is it put in dark energy, dark matter into the early universe about 20 million years after the Big Bang, and then just turned on gravity and physics and let it evolve over time in a small little segment. So this size, 250 megaparsecs for a side of this box, that's about 1/100th the radius of the observable universe. And what you see here is the red tendrils here are mapping out where the dark matter is. And over time, it starts out pretty uniform, and then it coalesces into this web structure, the so-called cosmic web, which is mapping out all the dark matter. You can see that you have these nodes. Where these nodes are, you're going to get super clusters of galaxies, and where there are little bright spots, you're going to get galaxies. This is telling us where the dark matter and the luminous matter follows the dark matter because gravity pulls it. So we're mapping out where the stuff in the universe is. You might think this is absolutely absurd. That's just a simulation made on a computer. We actually compare the results of this to the Sloan Digital Sky Survey, which mapped out over 1 million galaxies in our observable universe, where they are, and compared the simulated universe to the observed universe, dead on statistical match. And one of the inputs to that is how much dark energy and how much dark matter, which helps us narrow down the amount of dark energy in dark matter. I know, your head's probably reeling, mine is too. So let's end this long video with a movie where we fly through the Bolshoi simulation. I'm going to go ahead and hit play. So here is just a sphere of the Bolshoi simulation. What we're looking at are knots of dark matter, and this is where the luminous matter will follow. So this is where you'd see your galaxies and your clusters of galaxies. And what we're going to do is we're going to start flying through it so we can see this cosmic web, what it looks like up close. So here we go. We're just diving into a small simulated part of the universe, which we know matches the structure we observe. So now you can see some of those knots of dark matter. And as we get closer and closer in, you can see that each one of those little knots would be a galaxy. And you have that big galaxy in the center with all these small satellite galaxies moving around it. And we can see some of the structure in detail of this cosmic web. So if you've ever wondered what the universe looks like, here you are. If you've ever wondered what stuff is made out of, we've covered what matter is. We've even covered that there's this other dark matter. And to make it all work and make our universe understand, there must be some energy we haven't accounted for as well, so-called dark energy. So all the matter that we know and ever interacted with is just 5% of the universe. And notice, this didn't really end up answering the question of what is matter. I stopped at, we have the fundamental particles as predicted by the standard model of physics, but what is a quark? Is there something out there we could invent where we could smash a quark down into smaller bits? As far as we can tell, the answer is no by our modern physics. Our modern physics predicts the quark. But what is a quark? That's still kind of a weird question. What is the nature of a quark? So even though we did break this down, there is a lot of mystery there. And this is going to end my series of sort of the heady videos of what is space, what is matter. If requested, I might make a short video about what is time, but that is just hard. But if it's requested as one of the weekly video requests, then I'll go ahead and make it. And I'll go ahead and end this very long video. I hope you really enjoyed these kind of weird, simple, yet profound questions of what is matter, what is space. Thanks.